let's just walk through this real quick, the questions, because there is something to knowing kind of the typical kinds of questions, because it does kind of repeat from year to year. There's the free response is more about the big ideas of calculus, and those tend to show up over and over again. So this one talks about grass clippings in a bin where they decompose. Talks about the amount in the bin. So, we always have amount function, rate function, position, velocity, acceleration, that kind of relationship. So this is an amount where it's in pounds. So then they talk about average rate of change, right? That slope between 2 points. Talks about doing a derivative with that. This is a calculator one. This is something we're not quite ready to do yet. Finding the amount, find when the amount is equal to the average amount. That's something we haven't talked about yet, so that's something. And then it says L is a linear approximation. That's basically a tangent line. That's what a linear approximation is at t equals 30. So in other words, what they're saying is once you get past 30, this equation doesn't work very well. This is an exponential, so it's going up, 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 and then at 30 it switches and goes to a linear situation. And then they have you find, so basically you find that tangent line and when will that happen? Okay, so some tangent line stuff, rate of change stuff was in that problem. Here's what a big part of what we're going to do the second half of the year, areas, regions like that. So that's not for us, but there's always a problem like that. One of the 6 free responses is always about an area of a region, and a 3-dimensional solid, which we'll get into later. That's a big part of stuff we learn later on. Here's a graph of F, and it's going to ask you, actually, a lot of times they give you a graph of F prime and ask you questions about F, and that's stuff we did early on, and chart stuff, that's kind of chart kind of questions. Here they give you a graph of F, but then G is the big F. Now, we don't understand this notation yet with this integral here, notation, but what we'll learn is that basically means the antiderivative. And so basically they ask you a bunch of questions about G, which is like asking you about big F. So they give you little f, they ask you about big F. Well, that's the same as giving you F prime and asking about F. Okay, so we'll skip that one for right now. Okay, here's one I want to look at. So almost always one of them is a table of data. They almost always give you one like that. So they give them to you as functions, equations. They'll give you graphs. And they usually give you a table of data. So let's look at this one here. So it talks about train A. At these minutes, this is its velocity. It's going east and west. Okay. Find the average acceleration of train A. So part A here. Go ahead and do that real quick. This is a no calculator problem right here. Okay, we are into the no calculator section. Average acceleration. All right, what do you got? Anybody? What are they asking for? Average acceleration. What do they mean? How much? Make it too hard. When we hear the word average, now this will change a little bit later on. When we hear the word average, what's it going to be about? Slope between 2 points. Average rate of change. Now maybe it confused you because it said acceleration. But if you do slope between the 2 points in this table, what are you going to have? If you do the y's divided by the x's, isn't that going to be meters per minute per minute? Isn't that going to be acceleration? Average velocity, you take the position function and do slope between 2 points. That's how we do average velocity. You take the position function and you'd have meters over minutes, meters per minute. For average acceleration, you take the acceleration function, or excuse me, the velocity function, and you do slope between 2 points. So it's simply negative 120 minus 100 over 8 minus 2, because this is meters per minute divided by minutes. That's meters per minute per minute. You don't even need to simplify it, but it would simplify that. Okay? On the test in 2014, that was worth 1 point. Remember, this whole question would be worth 9. Okay? Average means average rate of change. They don't always say average rate of change, but if we're talking about position, velocity, acceleration, if they say average acceleration, that's the velocity function. Okay, the velocity, if we were doing instantaneous acceleration, we do the derivative of the velocity function. If you want to do average acceleration, you do the slope between 2 points of the velocity function. Okay, same idea. So you're just going to take and do that. And they'll want to, well, they didn't give any points for your supporting work. They only gave 1. Sometimes they would give 2 there. They want to, now they do a pretty good job of saying show your work. Do the data in the table support the conclusion that the train's velocity is negative 100 meters per minute at some time between 5 and 8? This question, another one, was really the reason I wanted to look at this too, was why? Intermediate value theorem, the IVT, right? We just talked about. So these theorems, that's one of the reasons we do these theorems, is these theorems do show up on the AP test because the function is differentiable. Since it's differentiable, it's continuous. Its differentiability guarantees continuity. So since it's continuous on a closed interval, 5 to 8, I mean, they left the interval open, but we know what the values are at 5 and 8, so we're fine. Okay? But it's always differentiable. Then we know it goes from 40 to negative 120. It has to hit every y value in between. So it has to be negative 100 at some point in there. And so you should say the words intermediate value theorem in your answer. Okay? Let's see. That one, C, we can't do. And B, we'll skip over that. Or D, we'll skip over that. Okay. This one. So now this is kind of new. This was I don't want to say controversial. It had some people, especially people that have a little more traditional textbooks, kind of up in arms a little bit. I remember when they put this on there. That's the first time they had really a problem like this. Now, our book, I think, prepares, one of the reasons I like our book, prepares us for these kinds of questions. I think we do more of this kind of stuff. Okay, so F and G are twice differentiable functions, so whenever you see that, you're just like, okay, that's good. I don't have to worry about sharp points. I don't have to worry about undefined. I mean, so when you see that, that's a good thing. Okay, find the x-coordinate of a relative minimum on the interval -2 to 3. So here's -2 to 3, so the whole interval. And we're talking about F. So we're just talking about F up here. So when you're looking for a relative or local min, what's the first thing you should think about? Forget this table. If you're looking for a local min, what's the first thing you think of? Derivative 0, right? If I give you a graph of f prime, the first thing you look at is the x-axis, right? Where's it cross the x-axis? So if I'm looking for local minimum, the first thing I better look at is where's f prime 0, right? Where's f prime 0? So I need that. And then, of course, to be a minimum, it's got to go what? Negative and positive. So see how it's given the same information, just in a different way? So right here at 1, f prime is going from negative to positive, okay? And it's a 0. But if there would have been, see, that happens down here. Well, not really, I guess they have 0. But if there wouldn't have been a 0 there, right, then we wouldn't have been able to use that. So even though it would have went negative to positive, there's not a 0 there, okay? Now, it'd have to be something. I mean, they'd have to do something weird with this. How does it do that if it's differentiable? But anyway, so, but part B I want you to look at. Explain why there must be a value C between -1 and 1 such that f double prime equals 0. Why must there be a value of c such that f double prime equals 0? Between -1 and 1. That's the mean value theorem. Now it's f double prime, right? So what function are we talking about? What function do we want to check the slope between the endpoints? F prime, right? Remember, mean value theorem says the slope between the endpoints of f, there has to be some point where f prime, where it has that derivative, right? Some point. Well, now they said f double prime, so that means the slope between the endpoints on f prime, there has to be some point of f double prime, where f double prime is that. Well, what would be the slope between the endpoints here on f prime? You got a value of 0 and a value of 0, right? So 0 minus 0 over 1 minus -1, 0 over 2. The slope on f prime between those endpoints, -1 to 1. So that's what you'd want to write down. You'd want to have something that looks like, and you should do this right now. This packet we're going to complete over the course of, the semester, right? I mean, so we're gonna pull it out from time to time. We'll do that with a couple of, as we learn new stuff, we'll come back to these and we'll work on it. So you'd want to have 0 minus 0, 1 minus -1, 0 over 2 equals 0. Now that's on f prime. So the slope between the endpoints of f prime is 0. So therefore, there must be some place in between there where f double prime is 0. That's the mean. So throw that on there, mean value theorem. Okay? So it's pretty obvious, both of those we recognize right away. Intermediate value theorem and mean value theorem. Okay? All right, so I want to look at that, and I think that might be it. Yeah, that's it. Okay, slope field, that's another one that's off and on there. I mean, we've done some of that, but difference equation stuff, if you got any questions, some of them come up in the packet, we can look at those. Okay, any questions, exam 2 or exam 3? This will be the last day, really, to go over any questions. So, exam 2, we did quite a few on exam 2 yesterday, if there's any left. But you started on exam 3 at all? Just the first 2. Okay. The sample ones, the ones we haven't talked about. Okay. Sample 1, sample 2. We're going to hand those in tomorrow before we start. And then the other 2 are due Monday. Other 2 are Monday. Okay, anything? On the third one. New one? The third one I gave you? Or no, the newest one. The newest one, exam 3. Okay, gotcha. 7, right here? Yeah. Yeah, again, this is another one of those, what you start noticing is, you get a number of them that are fairly routine, or I don't know about routine, but they look familiar, right? They look familiar. They look like problems we've done. Or now that you're into 3 and 4 packets of practice tests, you're seeing them more and more, right? And then you get these ones that are just kind of out of nowhere. And so here would be really I think, at least what's made sense to me, I haven't heard anybody come up with a better way, is recognition of that right there. When I see that and I realize they're talking about derivative, that makes me think of this. Right? You see the connection there? It makes me think of the definition of the derivative. Right? Now, the rest of the definition of the derivative is this, and then limit as h goes to 0. That's the definition of derivative. So I think what they were doing here is trying to test you on the definition of the derivative and your knowledge and recognition of it. Because if I take this and now put it into the language of this, right? Instead of X's, we would have A's, and instead of H's, we'd have B's, right? And so this would be the limit. So G prime of A would be the limit. I'm just taking all the X's out. The F's are getting replaced with G. The X's are getting replaced with A's. And the H's are getting replaced with B's. And I'm just writing the same thing. So the H's are getting replaced by B's. And so this would be G of A plus B minus G of A, and then all over B, right? So those two are identical. They're done magical by using X and H and F, right? This is the same thing. It's the same thing, okay? So, expect to see that? Maybe not. Maybe now you've seen it once, so maybe you see it again. So the more you've seen the definition of derivative, they'd like to, see that you, because it's a pretty important thing, right? The definition of derivative, everything we've done comes from that. So now, so then you start looking at this and you say, well, G, I could replace this up on top, right? If G of A plus B minus G of A is equal to this, I can just substitute that up top. So now I get limit B approaches 0, and I get 4AB plus 2B squared over B. And then all of a sudden it starts to kind of make sense. Because then it's like, oh yeah, limit. I could take out a B now on top. That would be 4A plus 2B all over B. The B's cancel. So now I have the limit as B approaches 0 of 4A plus 2B. Well, remember, that's what we did. Remember, we did these problems where we got the H to cancel? Well, now that you got the H to cancel, in this problem, the B to cancel, then what do? We can put a 0 in for B. So you put a 0 in for B, and that cancels that out. So G prime of A is 4A. So what's G prime of X? 4X. That's it. I mean, that's really, I think, how you do it. But the key was recognition. The key was looking at that and saying, hey, that looks like f of x plus h minus f of x. Okay. So, okay. What else? Yes, good. I was gonna, we did this the other day. We did that inverse function of remember where we had the 3, 9, the 9, 3, and we talked about the inverse thing and the reciprocal relationship and so forth. But we also talked about how we can do it with implicit. The one we did with implicit differentiation. So this is the same problem. So when you see inverse, if you're given one function and then they ask you about the derivative of its inverse, the other function, okay? Again, I'm going to go back to what I've said before. I always think of this as, okay, F will have this point and G will have some other point. Now, the difference here is they don't give you a point here, really. Actually, I take it back. Time out. I wouldn't do this because now I just realized, well, I probably would have started this way. Obviously, I just did. I would have started this way and said, wait a minute, they don't give me a point. They're not asking me for F prime of 2, right? So let's pretend for a minute that they were asking me for F prime of 2. Okay, so let's say that was the question. Well, if they were asking me for F prime of 2, I just said, okay, they're wanting to know when 2's an input on F. That tells me that 2 has to be an output on G. So my first step then would have been to put a 2 over here and then solve this for X. Then that would have given me that value, which would have given me this value up here, right? But that value, would have given me this value and this value, and then that would have been what. Then I could have done the derivative of this, right? I could have plugged in this number, and whatever slope I got, I could have done the reciprocal, and that would have been the one for F. Because remember, inverses have reciprocal slopes, okay? So I couldn't do this derivative and plug in a 2, though. That's the problem with that, right? I can't, because 2 is the input for F, not for G. So I needed to get this number here, so then I could do this derivative, put that number in, get that slope, then I could do the flip, and then that would be the one for the F at 2. Okay, so that's where I was going with that, because oftentimes that's what we get. But actually, this one's easier than that, because they just want F prime of X. So all we need is to find f of x. So we can just interchange our x and y here. So this is actually one of the rare ones you can do that, because usually on these problems where we have to attack it like I did is because we can't find the other function, right? I mean, in this problem, if this would have said f prime of 2, I actually could have found the f function, because we can do this. We can interchange the x and the y's, right? Here's how you do an inverse. Oops. You interchange the x and y's, now you solve for y. So this is g right here. This is going to be f up here. So we cube both sides, that'd be x cubed equals y minus 1, and then we add 1, and we get x cubed plus 1, right? So that is now the f function right there. So they want f prime of x, so now f prime is just x squared. I'm assuming that was the answer. No, I don't think they looked that one. And they looked that one. That was it. Okay, so that of the inverse ones, that is an option, right? That is something you can always try. If they give you a function and they talk about the inverse, you can interchange the x and y and try to solve for y, but you can't always do it. Now, the one we did the other day, we interchanged the x and y and did implicit differentiation on it, and that kind of worked. But we still had to find this 2. We still had to take that 2 that was an input on this one and make it the output of the other one. So we still had to do that. Okay, maybe we can, well, maybe that'll come up again. Because it could come up tomorrow, right? On one of them. All right. Anything else? Anything else?
Could you just run through that process again?
Of the inverse one? I tell you what. I've got one. I think I've got one here. Let's get one that's a little more straightforward. I might have to get back to it. Let's here we go. Okay. Yeah, let's do this. Let's look Well, here, we can do this one. Okay, so, oh yeah, right here. Okay, so let's do this left side right here. So this would be the kind of problem I was talking about. So they give you an f function, and they say g is the inverse, find g prime of 2. Okay, find g prime of 2. So when I'm given one of these, again, what always makes the most sense for me is just to kind of come over here and say, okay, the f function and the g function. G is going to have some point 2 something, right? And I know it's g. I know it's g prime I'm looking for, but I know the g function has an input of 2. That's what I'm talking about. That tells me the f has to have an output of 2. Okay, and that is the secret to these problems, is understanding that. Because once you understand that f then has to have an output of 2, that allows you to now set that equal to that. So you can now set the f function equal to 2. Now this would be a calculator one, probably. This particular one would be for sure. Now maybe if there's no calculator, the function would be easier to solve. Okay, because on this one, if we try to interchange the x and y, if we call this y over here, if we go x equals y cubed plus y, we can't solve that for y. Okay, now we could do the implicit differentiation thing. See, this is now the g function down here, because I've interchanged the x and y. So we could do implicit down here. But the problem is we'd still have to figure out what to plug in for y. Okay, because the x would be 2, but what would you plug in for y? Well, it'd be this right up here. Right? We'd still have to solve this for 2. So I'm not sure this gains us anything by doing it this way down here. Okay, so anyway, what do you get? Somebody got that? Put that in your calculator. X cubed plus x equals 2. Let's solve it. X equals 1? Okay, so we know that the point that is kind of the mirror point on this function is the point 1, 2, 2, 1. Okay? All right, now, so they want g prime of 2. So what you can do is find f prime of 1. Those are going to be the partner slopes, and the partner slopes are reciprocals with inverse. So that you got to remember that too, right? So we got to remember this thing with interchanging this, and then we got to remember that they're reciprocal. So f prime would be 3x squared plus 1. F prime would be 3x squared plus 1. We plug a 1 into there, we get 4. Right? So 3 times 1 plus 1 is 4. So therefore, what is g prime of 2? 1/4. Okay, so two key parts to that. One key part is the inverses. So they want g prime at 2, so g's an input of 2, g has to be an output of f, and so you find what the other point is there. And then understanding that now you can just do the derivative of this and get the f slope, but not at 2. It's got to be the f slope at 1. Find that, then the reciprocal of that will be the g slope at that partner point. Okay, 2 and 1 are like partners. Okay, so I don't know. I don't know if that helped any, James, but you know, those are the two big things to remember, the reciprocal slope. So now, if you had one like this, so this would just be another way of asking the same thing, really with a lot less work involved. They tell you that g of 1 is 3. So again, what I would do is I say, okay, on the g function, it's the point 1, 3. So on the f function, it's 3, 1. So they're telling me f prime of 3 is -4. Well, that's the f slope at 3. That's going to be a reciprocal of the g slope at 1. So we're going to have -1/4. Right? Now, it looks like a really confusing problem because they give you they tell you this, but then they tell you this. You're like, why is that helpful? They tell me g of 1 is 3. They want g prime of 1. And they tell me this thing. Why is that helpful? Well, it's helpful because of this right here. Okay, because of that we flip those. Okay, and then we know that they're reciprocals then. And there it is. Okay, so that second one could definitely be a question that they ask too. And the same thing. Okay. All right. So, and then I know Matt, you had said something about interchanging. You know, and this is what we did yesterday, where we did, or not yesterday, but the other day. And we thought, well, let's do this. This would be finding g prime right here, and that's fine. The only problem is you got to know what to plug in for your y here, right? Well, you don't know what to plug in for your y until you get that number, right? Until you set this equation equal to 2 and get that number. This is the x number on f, so it's the y number on g. And so when we put that in there, now we get this. So now we get 1 equals 3, that'd be 3y prime plus y prime, that'd be 4y prime. So we get y prime equals 1/4, which is the same thing. Okay, so the advantage, I suppose, of doing the interchange xy thing is you don't have to know about it being reciprocal, but you did have to know about finding this. Okay, it just worked out to be the reciprocal, so we were fine. Okay, but knowing they're the reciprocal is key to doing this one, so it's important. All right, that's a lot of time on a problem that's probably not, I mean, it might show up once, it'd be 1 point out of 31, but whatever, every point matters, I guess. All right, anything else? Anything else? As I think about this, I really think we've covered, or at least any of the tricky stuff that I ever worry about, you know, that maybe we haven't seen for a while. I mean, other than just like basic derivatives, we can do that, right? What's the derivative of 2 to the x? 2 to the x times ln2, right? I mean, you're going to get some of that stuff. This would be 4, we leave the inside alone, times the ln4, and then also times the derivative of the inside, which would be 2x, right? I mean, that kind of thing. I mean, just, you know, I feel like sometimes when we go over questions together, we focus on the really hard ones that nobody gets, and that's fine as long as there's the easier ones we are getting. If you're not, be sure and ask me if it's not making sense to you in the book. Okay. All right. So I'm gonna let you work. Come up and ask questions. Get a lot of stuff done in these packets. I know it's a lot. Sometimes you get to feel like maybe busy work a little bit because you're doing the same problems over and over. But I really don't think it is. I'll be honest, I'm not a fan of busy work for busy work. I really think over time, my goal is for you to go into calculus next year and just be awesome and just remember stuff and long-term understand what's going on. And so, and I really think this helps with that. Okay, so that's my goal. Okay. So midterms the next 2 days, and then Tuesday we jump into areas. We'll get going on the second half of Cal. So. Yes.
Calculators.
Calculator one tomorrow. Yes. So make sure calculators are charged. If you don't forget about how to solve on a calculator, how to put the vertical bar if you need to restrict a solve, to a certain interval. On the trig ones especially, again, on the free response, you have to show your work. If you're doing a max or min or something like that, you got to do your setup. If you're doing slope between 2 points, write it down, even if you're using your calculator to do it. Okay, 3 decimal places always for your answers on the multiple choice or on the free response. Okay. I did forget one other thing I wanted to talk about, and this would be a no calculator probably scenario, and it gets into some algebra. Okay, so if I gave you a function like this, you don't want to FOIL that out, right? I mean, that would be really a mess, and then being able to solve it would be ugly. So if a question said, hey, what are the stationary points or what's the local extrema, you'd want to do the derivative set equal to 0. So you do a product, right? So I'm just going to run through real quick. I'll leave it up here later if you want to copy it or anything. But so derivative of the first, you bring down the 3, leave that alone to the second, times the derivative of the sides of 2, leave the 4x plus 2 alone. Then leave this alone, and derivative of this is 4. Okay? Now, what can you do to do this? You don't want to FOIL these out, right? So what can you do? You've got 2 of these red things, and you got 3 of these red things, so we can take out how many? We can take out 2 of them, right? Now you can take out some other stuff with the 4, but I'm not going to mess with that. So I'm going to take out 2x minus 5 to the second. Now when I do that, these are gone, and 2 of those are gone, and so I just have 1 left. And now we just go ahead and distribute and combine like terms. I end up with that, and sure enough, now we can solve it where this is 0 would be 5 halves, where this is 0 would be 8 over 32 1/4, right? So just algebra in solving. So just understand that when you get a quantity to a power that you could do that. Now, where that gets tricky, though, see, that's not bad. But where that gets tricky then, or trickier, is when you get a fractional power. Okay? But it's the same exact thing. So I'm going to do product rule. So I'm going to bring the 1/2 down, times this, whoops, I forgot my 2, and then drop that to a negative 1/2 times the derivative inside is 2, okay, 4x plus 2 left alone, and then this left alone, then the 4. Okay, now, when I get down, come on. This is so hard that my mini was losing. Okay. All right, so now the question is, and so this would actually cancel out 1/2. But now the question is, how many of these can you pull out? Right here. What can you factor out? Right? It's easy with just whole numbers. Well, if you have 2 and you have 3, how many did we pull out? The littler number, right? Well, that's what we want to do here. So we have a negative 1/2 of these, which seems weird to say, and 1/2 of these. We pull out the littler number, which is the negative 1/2. Okay? So we pull out the negative 1/2. That's 1/2. So we pull out a 2x minus 5 to the negative 1/2. Now, that leaves us just the 4x plus 2 on this one. But what's it leave us here? Well, what did we do on the other one? We had 3 of them, and we took out what? 2. We subtracted those powers, right? That's what we did. Now, we just do it in our head, don't think about it. But we subtracted those powers. So what's happening here is if I have a 1/2 of them, and I took out how many? Negative half, right? I took away negative half. Well, what is that? 1. It almost always works out that way. Well, here's why it always works out that way, is one of them is a derivative, so you dropped it by 1. The other one you left alone, so they're always going to be 1 apart when you have a problem like this. So what happens is, you're going to, when you take out a 2x minus 5 to the negative 1/2, you're going to, from a 1/2, you're going to be left with just 1 2x minus 5. And then that 4. Okay? And then away you go. And so you'll have this and so forth. And so, well, I guess away you go. Maybe I should finish it because something interesting does happen here. So you get this. Okay, so you get 2x minus 5 to the negative 1/2. And then here you get 12x minus 18. Now, you got to be careful because this is a negative power, which means it's really where? On the bottom. So what you have is 12x minus 18 over 2x minus 5 to the 1/2. Now where does a fraction equal 0? When the top is 0, so your stationary point would be at 18 over 12 or 3/2, right? So your stationary point would be there, but this would be what? This would be where the derivative is undefined, but you have to check that for like a local max or min, right? So you would take your 3/2, which you get when the top is 0, and here it'd be 5/2 would be where the derivative is undefined, and there might be a sharp point there, which could still be a local max or min. So on your number line, you'd have to put both of those, okay? So that gets a little bit trickier, but I just want to point out that algebra there when you get a fraction like that. Just understand when you pull out that smaller one, what's left is you just subtract the power. But it should always come out to be 1 on these derivative forms. Okay? All right.
This